Okay, it's 5:30, so let's go ahead and get started. Good evening, everybody. How's everybody doing today? Yes, hope everyone's safe. Yes.
Yeah, it's getting crazy.
Yeah, it's I'm not sure where you guys are at, but it's a little bit scary outside right now. I've been hearing a lot of neighborhoods around here, but starting to evacuate. So if you guys get the order to evacuate, definitely just drop everything and just get out of here. So remember, the lectures are going to be posted online, so you're not going to miss out on anything. So please just make sure that everyone just stays safe. Okay. So I might be asked to evacuate halfway through this lecture today too, because I've been hearing that some neighborhoods around here are evacuating. So if that's the case, if I have to cut this short, I'll finish this lecture, whatever is left, kind of asynchronously, and I'll post the video on YouTube, just like I usually do. Okay. Okay. So the topic today is going to be how to implement finite element codes doing these 1D boundary value problems. Okay. So you might have noticed that I've posted the lecture slides on Canvas. I almost always say titanium. And I've also posted the starter code for today. So that's what we're going to be working on primarily today. And so if you guys want to go to the Canvas site and download them, so you can find them on the week 10 of our course organizer. And so besides that, I have a couple announcements. So while you guys are downloading that, I was able to grade your ANSYS activity 2 yesterday. So finally, I know it was I was a little slow on that. And so you should see your grade for that on Canvas right now. And I've also posted the solutions for that too. So the ones that I mostly look at for the problems that I mostly looked at for ANSYS activity 2 was a problem 7 and 8, which is our frame code and our truss code. So the solutions for that you should see on Canvas there too. So if I make comments about your code, or if you wanted to see how I implemented it, then definitely take a look, and that's good to reference, especially going forward. As we're doing a lot of this stuff right now, we're going to be doing a lot more MATLAB stuff. So it's really important that you guys kind of stay up to date on kind of the MATLAB stuff, because it's going to help you out with the project. So so another announcement. So there was a typo in one of my solutions for homework 3. So a couple people pointed that out to me over the weekend. So I think the problem was problem 4B. So it was the last kind of finite element forms, the very, very last problem on the homework. So I've corrected that error, and I've uploaded kind of the correct solution onto Canvas. So you can check that out. If you were getting a different answer than me on problem 4B, definitely check out the updated PDF, because that one has the more correct solution. Okay. So before we get started, are there any questions I can answer? Okay. All right. So I'm gonna go ahead and share my screen. Right. And so the topic for today is going to be these lecture slides that you have posted. So let me just show you where they are. Okay. And so if you go to our course website, if this bar would get out of the way, thank you. Okay. So here's our course website here, right? And so if you go to week 10 for our class right here, right? So you should see the lecture slides right here. So you can see implementing a 1D boundary value code lecture slide. So that's the slides we're going to walk through today. And what the slides are going to do is it's going to walk you through, what you need to implement into the starter code. And so the main, you can download the slides if you want. So I'm going to have them on my screen here. But the main thing I want you guys to have open is the starter code. So go ahead and download this. It'll be you can see it's a .m file. You can download it to your computer, and then you can open it up in MATLAB. So today's going to be kind of an interactive session. So if you can follow along, and fill in stuff as we're kind of filling it in together, that's really going to help you out down the line. Okay, so go ahead and download that and open up MATLAB, and then from there we'll get started. Okay. Okay. And so here are the slides. Okay, so the slides, remember, they're just going to be our guide for this and to kind of organize the lecture today. Right? Okay, so just a brief introduction. So, for the last few weeks, or last couple of weeks, we've been learning, kind of a different way to do these finite element problems. So we started with the strong form, and then we went to the weak form, and then we went to the finite element form. Okay, and so the whole idea behind these past couple of weeks is that we can, the finite element method is not something that we can just use to solve structural problems, which is what we did in the first half of the class. Really, what finite elements is a method to solve just any kind of differential equation on a domain. Okay, and remember what we called these was called boundary value problems. And what makes a boundary value problem is that you have a governing differential equation. And so we've only done 1D so far. So in 1D, it's just an ordinary differential equation. But in 2D and 3D, we'll start to have partial differential equations. Okay? And then the other part of the boundary value problem is the boundary conditions themselves. Okay? And so we've seen kind of two kinds of this. So we've seen Dirichlet boundary conditions and Neumann boundary conditions. Okay. Okay. And so back in the first half of the class, we went over this code, or we went over a code on how to solve kind of frame problems, and then eventually you guys did on your own truss problems using MATLAB. Okay. And so we're going to build on a lot of those fundamentals that we built on that last one in order to implement this code right here, which is for 1D boundary value problems, right? And so, you know, I've kind of chosen the order kind of very particularly because, you know, we started out with kind of the structural problems, which we kind of did to death. And the MATLAB code was kind of a reflection of that process. And so now we're taking kind of another step here to boundary value problems where, you know, we're going to write a code that's a little bit more generic. And so, you know, there's less that we can kind of see and kind of touch with it, but we want to write this code in kind of a general way that it can solve these kinds of problems, right? And so this code right here, you know, a lot of the standards and a lot of the format of the code and the structure, that's going to tie directly into your projects, which I'm going to be working on this week as well. Okay. And in particular for this 1D problem, you know, one nice thing is that when you have a one-dimensional problem like this, you can actually just plot the results. And so this will be kind of a nice change because I know in our structural problems, the way we viewed the results was that we just viewed kind of the nodal solutions. We said that this was the x displacement, the y displacement, the rotation at these nodes. And that's, you know, not always the funnest thing to look at because you're just staring at a bunch of numbers. But with the 1D problem, you can actually plot the results, and it's, you know, a lot more easy to visualize. Okay. Okay. And so in this code, we're going to be solving the following problems. And this is kind of the parameters that we're solving for. And so we're going to be doing a 1D heat transfer problem. And so our 1D heat transfer problem is given by this geometry where we have a rod. And on the left-hand side of the rod, we have a fixed temperature T naught. And T naught, you can see here, is given by 25 degrees C. Okay. And so that's our Dirichlet boundary condition on the left-hand side at x is equal to 0. And on the right-hand side at x is equal to L, we have a Neumann boundary conditions with an outflux of 600 watts per meter squared. Okay. We have the thermal conductivity, and so I kind of made this diagram to be generic in case, you know, you might have you know, a thermal conductivity that changes with x, but in this case we just have you know, a thermal conductivity is constant, so it's just 50 watts per meter degree C. Okay. And our area is also a constant. So again, I have area as a function of x, but just for this example, I'm going to have area be constant. So area is going to be 0.1 meters squared. Okay. And in addition to that, we have some thermal generation. So remember, our thermal generation is given by s of x, and our s of x is going to be just the function x squared. All right. And so if you solve this problem exactly, so if you basically, you know, take the strong form of the equation, or even the weak form too, you can solve, and you can find the exact solution. And so the exact solution in this case is given by this function, t of x is equal to minus 1 over 60, x to the fourth plus 61 over 5x plus 25. Right? And so you might be asking, you know, why are we writing a code to solve a problem that has an exact solution? And the answer to that is these are the perfect kinds of codes to write. These are the perfect kinds of codes to write, especially when you're first learning these things, because, you know, if you know the exact solution, you can check your computed solution against the exact one. And if they don't match, then you know there's something wrong with your code. Okay? Because when you're developing code for the first time, if you don't really have a reference for, you know, what you're solving for, it's really difficult to know whether your code is right or not. Okay. And so for this activity, you know, we're solving a problem that we already know the answer to, mostly just to learn kind of the fundamentals of writing these kinds of codes. Okay. Okay. Are there any questions on this so far? Okay. Okay, and so now let's kind of walk through the code and do each of the parts here. Okay, and so the first section of the code will be this top section right here. And so in this top section, you know, we're going to define our problem parameters. Okay, and so you can see I have a parameter here for the length of the rod. I have a parameter here for the thermal conductivity. I have a parameter here for the area. One for the Dirichlet boundary condition, one for the Neumann boundary condition, and one for the number of elements. Okay. And so I'll talk about the number of elements in a bit, But why don't you guys go ahead and open up your code and go ahead and fill in the rest of the, go ahead and fill in the quantities up here, okay? And so you can see here we have a length of 5, so we can go ahead and hit a 5 right here, okay? We have a thermal conductivity, which is 50, okay? Next, we have our area, and our area is 0.1. Our T naught is going to be 25, okay? And our Q out is going to be 600, okay? Okay. And so the first section of the code, is usually pretty simple. We just are filling in our properties. But the nice thing about this code is that, since we don't have to define them element by element like we did in the truss code or in the frame code, we can just kind of define them all at the top right here. So this part is a little bit more convenient than the last one. Okay. Okay. And so the last thing, the last parameter that we need to set is the number of elements right here. Okay. And so the number of elements basically describes how finely we're going to discretize our domain, okay? And so you remember for 1D problems, we have kind of a line that goes just like this, right? And how many elements that we can break up the domain in, generally is up to you. It's up to you, except when it's not. When I want you to get a certain answer. So, but in this problem, I'm actually going to leave it up to you. Okay, so you can decide how many elements you want to break up this line into. Okay. So in this figure here, you can see I have 11 elements, and so 11 is perfectly fine, if you want to do 11 elements, but basically anything between 5 and 50 would be good just for this example, okay? And so I'll leave that up to you. So I'm going to do 10, just because 10 is kind of a nice number, but whatever you choose for this problem, it's actually going to give you, hopefully the same result at the end, okay? Okay, are there any questions in this, or is everyone able to fill in kind of this top section right here with the properties? Okay. Okay. And so before we move on, I do want to make a comment about something that's missing from this code that was in our last one. Okay. And so that thing that's missing, that as you can see from the slide right here, is the connectivity matrix, right? And so remember last time in order to solve our truss and frame problems, we had to define our connectivity. And what the connectivity did was it specified which nodes were connected to which elements, right? And so remember, when we were doing our bicycle frame problem, we had to define our connectivity. It said element A or element 1 was connected to nodes 1 and 3, okay? And so that was really important, and that was important for our assembly, right? So just to make sure that we can insert our element stiffness matrices into the right locations, our connectivity matrix basically helped us out with this, okay? And so in this starter code that I'm giving you, you'll notice that there's no connectivity matrix. And that's, something that's unique to this 1D problem, but for your project and for any 2D problems, you're going to have a connectivity, okay? And so, the reason we don't have it here is because we just have a 1D line, and actually the connectivity is really simple, right? And so if you look at element 1 right here, element 1 is connected to nodes 1 and 2, okay? Element 2 is connected to nodes 2 and 3, 3 is connected to 3 and 4, and so you can start to see a pattern here, right? And so our connectivity, we can define as these kind of this simple relationship right here, where we have an element I, so I can be anything from 1 to the number of elements, okay? And so in order to get the left node for this element, we just take the element index I, okay? And so you can see here, like if we choose like element 7, then the left node will be node 7, okay? And then the right node will just be I plus 1, okay? And so you can see again, if we have a random element 7, we take 7 plus 1, which is 8, and that's going to be the rightmost node, okay? And so in this particular case, because our geometry is so simple, we don't need a connectivity matrix. And so we can just kind of just off the top of our heads know which nodes are connected to the elements. But this is something that's unique to 1D problems. So normally for like any 2D problems, you're going to have a connectivity matrix. So I just want to put this here just to kind of remind you, what the connectivity matrix is and why that's going to be important down the road. Okay. Okay. And so the next step is going to be our data containers, okay? And so just like we saw in the previous frame and truss codes, we have to create variables to store our matrices, okay? And so you can see here we have our K global, so this is going to be our element stiffness matrix. We have our F global, which is our global forcing vector. We have KLM, which is going to be our element stiffness matrices, and FLM, and so this guy is fairly new, and this is going to be the element forcing vector associated with the elements, okay? And so what I want you to notice here is I want you to take note of all the different sizes of these systems, okay? And so first you see here that K global, which is our global stiffness matrix, the size of this is going to be number of elements plus 1 by number of elements plus 1, okay? Because remember, the global stiffness matrix has to be sized by the number of nodes in our mesh, okay? And so you can see here, you know, in a simple 1D case, the number of nodes that we have is simply just going to be number of elements plus 1, okay? So if we have 11 elements, then we're going to have 12 nodes. If we have 5 elements, we're going to have 6 nodes. And so that's why we have that there. And then same for F global. So F global here would just be number of elements plus 1 by 1, okay? All right. And then we come to our element stiffness matrix. So our element stiffness matrix is going to be 2 by 2 for this simple 1D case. And then we need to store n of them, okay? And so we need to have an element stiffness matrix for every element. So that's why we have this kind of 3-dimensional stack of matrices like that, okay? And then same thing for FLM. So FLM is just going to be a 2 by 1 vector, but we need to store one for every single element. So we have to size these by n and len right here, okay? All right, any questions on this so far? All right. So far, pretty straightforward, hopefully. Okay. Okay, and so the next thing is this is kind of the first thing that I want you to really implement. Okay, and so there's 2 variables here that I need you to implement. So the first is going to be pos vector. Okay, and so pos vector. So the pos stands for position. Okay, and so what this vector is going to be is it's going to be a list of the coordinates for each of the nodes. Okay, and so one thing that we're going to need once we start filling in our element stiffness matrix and element forcing vectors is we're going to need to know the positions of every single node, okay? And that's what's going to be stored in here. And so, you know, the way that we can do this is we can use a special MATLAB function called linspace, okay? And so if you've never used linspace before, it's a function that takes 3 arguments, okay? So let's go ahead and fill in linspace. Okay. And so the 3 arguments are going to be x start, xn, and number of points, okay? And so what this function will do is that it'll create a vector that has n points, number of points, okay? And so if we say, if we make the last argument 10, then linspace will make a vector that has, you know, 10 entries, okay? And then what these 10 entries are gonna be is that, you know, they're gonna be, you know, numbers that starts at x start and ends at x end, okay? And then everything in between will basically be evenly spaced points in between x start and x end, okay? And so let's do an example. So let's say that we chose a number of points to be 5, okay? And then we chose our x start and x end to be 0 and 5, okay? And so let's say we do 0, 5, and then 5, okay? Okay, and so what this is going to do is going to create a vector that has 5 entries. Okay, so we're going to have, you know, a vector that looks like this. And there's going to be 5 entries. Okay, and so the first entry is going to be 0, and the last entry is going to be 5. Okay, and then in between here, we're going to have 3 more points. Okay, all right. And so the rest of these 3 points are going to be basically evenly spaced parts right here. Okay, and so in this particular case, they're going to be spaced just like this. Okay. Right. So they're going to be 1.25, 2.5, 3.75, okay, and then 5. Right. And so what you can see from this command here is that, you know, our starting point is going to be 0, and that's what we have here. Our ending point is 5. Okay, and so that's what the second entry does. And then 5 right here, this determines the length of this array. So maybe I could have chose a better example instead of 2 5s, but, you know, hopefully that distinction is clear to everyone, where this first number 5 right here denotes the ending point, and then the last 5 right here, that determines the size of this vector right here. Okay. Okay, and so basically what we want is we basically want to use this linspace command to basically give us the positions of every node in our line. Okay. And so you can see from the figure right here that the that the starting location here should be 0, okay, because that's our starting point, and our ending location here should be L, okay, right? And so L defines the length, so that's going to be the coordinate of the last point right here, right? So we want the coordinate of this last point to be the length of our bar, okay? And then finally, we need to put an entry right here, okay? And so how many, using the variables that we have right now, okay? And by variables, I mean the stuff that's up here. Go ahead and fill in kind of the last entry for this Lin space vector, okay? All right. So was everyone able to fill in the that last entry right here? So you should use a variable that's up here, and then you have to modify it a little bit. Okay. Okay. And so what you should have done, you should have done NLM, right? So that's the number of elements, but we have to add 1 to it, right? And because remember, you know, we have a variable that tracks number of elements, but the number of nodes is always going to be number of elements plus 1. And so that's why we add NLM plus 1. Okay. Okay. And then the last thing that we need to do is we need to specify the length of the element. Okay. Length of each element. So what we're basically implicitly assuming is that each of these elements are the same size, which is, you know, a pretty reasonable assumption most of the time. And just so it's convenient for our calculations later, it'll be nice to save the length of each of the elements. Okay. And so there's a number of ways that you can do this. And so one way that you can simply do is you can just take the length and divide it by the number of elements. Okay. Right. So that's one way you can do it. And so another way that you can do it that uses actually this pos vector that we just did, okay, is you can just take the difference in between the first 2 entries. Okay. Right. And so what this will do is it'll take the coordinate for the second entry in pos vector and subtract the coordinate from the first entry, and that will give you the length of each of the elements because each of the elements have the same length. Okay. And so you can do either one. Either one gives you the exact same thing. Okay. All right, any questions on that before we move on to the element stiffness matrix? Okay. Okay, and so the next step is going to be the element stiffness matrix, right? And so, you know, we know for these problems, you know, the way that we form the element stiffness matrix is by computing this integral right here. So we have a 2×1 vector of the shape function derivative dn1 dx, dn2 dx, and then to that we're going to multiply our thermal conductivity and our area, so Ka, okay? And then we multiply that by a row vector 1/2 of the shape function derivatives, okay? So dn1 dx, dn2 dx, okay? And so what we're going to do is we're basically going to implement this integral here into the code. And so for this part, we're pretty blessed because the thermal conductivity and the area are simply going to be constants, and so we can just take them out of the integral, okay? Okay, so first let's start by computing the shape function derivatives, and that's what I have right here for you, okay? And so we know from our notes from before that dn1 dx is going to be minus 1 over LE, and dn2 dx is going to be 1 over LE, okay? And so I'll give you guys a couple minutes, so why don't you guys go ahead and fill in the code to compute dn1 and dn2, okay? And then also to fill in the codes for the column vector, and so the column vector being this guy right here, okay? And then also the row vector, which is going to be this guy on the right here. And then from those, we can compute kind of our first 2×2 matrix by just multiplying those 2 vectors together, okay? So why don't you guys go ahead and fill that in, and I'll give you guys a couple minutes to do that. Right, so the question is this code is not equipped to handle KAs as functions, so that's right. And so that's actually going to be your homework. And so that's going to be a homework that's going to be assigned, that's going to be tacked onto the next ANSYS activity, I think. Or I might have one more in between that, where I want you guys to implement a code where you do factor in like if an area can change as a function of X. But for now, you can just assume that it's constants. Yeah. Mm-hmm. Okay. So was everyone able to fill in that that part of the code? And so this one I won't fill in for you guys because I want you guys to kind of this is kind of the the ones I filled in for you up above, that was kind of just bookkeeping and just organizing the code, but this is where we kind of apply the theory that we've done before. So I'm not going to fill this part in for you. But was everyone able at least to get like a good guess for what to put in for these lines of code here? Right. Okay. And so that's going to be our shape function derivatives, and then this is going to be our starting 2x2 matrix. Okay. And so after we do that, we have a system now that looks like this. We have our element stiffness matrix is equal to this 2x2, which we just formed right here, and then multiplied by the integral from x1 to x2 of k times a dx. Okay. And so just like Eric kind of mentioned, all of these, this k and a are going to be constants. We can just take them out of the integral. And so when we take them out of the integral, we just have the integral from x1 to x2 dx. Okay. And so when you integrate those guys out, then you simply just get the length of the element, which is just to be x2 minus x1. Okay. And so what I want you to do here is in this line of code, line 44, I want you to modify this KE in order to account for the thermal conductivity and the area, okay, and also for the integral. And then in line 47, what I want you to do is to store this element stiffness matrix into our KLM. Okay, so remember our KLM here is our data structure that we're using to store our element stiffness matrices. Okay, and so if you're wondering what to do for this code, you can look at kind of our previous codes for the frame and the truss to fill that one in. Okay. And so once you guys go ahead and fill in kind of these two lines, first KE, which you get from multiplying K and A and the length of the element, and then go ahead and store this element into KLM, all right? All right, was everyone able to fill in those lines of code? So it shouldn't be too much code there. So it's not that much to write. Okay. So the nice thing about this code is that it's a lot shorter than our frame code, because there's a lot less things that we have to hard code in. So if you remember from our frame code, we had to plug in basically all 36 entries of the element stiffness matrix. And so here we only have a 2x2, which is only 4 entries. And a lot of it actually we can compute just by performing matrix and vector multiplication. So it's going to be a lot shorter of a code, but the next part will be tricky because we're gonna do Gauss quadrature integration. Okay. And so the fact that no one's in the chat, I'm going to assume that everyone's got this part. So we're going to go ahead and move on. Okay. And so the next part is going to be our element forcing vector. Okay. And so if you remember from the notes, our element forcing vector is given by this. And so we have integral from x1 to x2 of our shape functions n1 and n2 times our heat generation term s of x dx plus our Neumann boundary conditions. Okay. And so we're going to tackle kind of both of these terms kind of individually. So we're going to start with just the heat generation term, okay? And then after that, we're going to apply our Neumann boundary condition. So it'll all be handled within this loop, and then from there, we'll have our element forcing vector, okay? And so if we plug in basically for this function right here, so we plug in n1 of x times n2 of x, right? Then we get this expression right here. So I've already kind of simplified it for you. So n1 of x is going to be x2 minus x over the length of the element. So I've factored out 1 over LE. So that's why this factors out in front. And then n2 of x is going to be x minus x1 over LE. Okay, so I've already kind of filled those in for you. And then for this particular problem, our s of x is going to be x squared. Okay, and so what we're evaluating basically is just this integral. So we're basically going to be doing 2, right? And so if we multiply this x squared through each of the terms here, we have integral from x1 to x2 of x squared x2 minus x cubed. And then for the second entry, we have x cubed minus x1 x squared, okay? And so, for a problem like this, I know that we can just perform this integration by hand, but, this is the perfect opportunity to practice Gauss Quadrature, which is something that's going to be, really, really important, okay? And so what we're going to do is we're going to implement the code that evaluates this integral using Gauss Quadrature. Okay, and so I'll kind of walk you through step by step, all right? And so if you remember from Gauss Quadrature, the first step is going to be to decide how many Gauss points that we want to use, okay? And so for this problem, we're going to use 2 Gauss points, okay? And so that's what I've denoted here as GP1 and GP2, okay? And so, the first thing is we need to define the Gauss point locations, okay? And so you're going to need to look back in the notes. So actually, let me pull up the notes right now. Okay. Come all the way down, okay? All right, so you can see from this table right here, the number of Gauss points is going to be 2 right here. And then the locations for the Gauss points are going to be given by this table right here. So we have 1 Gauss point, so that's going to be minus 1 over root 3. And then the other Gauss point is going to be 1 over root 3, okay? And so I'll go ahead and fill this in for you. So we're going to have GP1 is going to be minus 1 divided by square root of 3, okay? And then GP2 is going to be 1 over square root of 3, okay? Right, so those are our Gauss point locations, okay? Okay. And so those are our Gauss points. And so the next thing that we need to input is we need to input the nodal coordinates, okay? Because, after we get the Gauss points, we know that we need to form this function right here. So remember this function right here, which is x as a function of, and I found out this symbol was actually called psi, okay? So that's xi. And so it's no longer tornado. I'll try to call it by its proper name. And so x of xi is going to be x1 plus n1 of xi plus x2 n2 of xi, okay? And this formula right here is going to be crucial for us to apply our Gauss quadrature, okay? But in order to apply this, we need to know the coordinates of the elements, okay? So we need to know x1, which is the coordinate of the left node, and then x2, which is the coordinate of the right node, okay? And so in order to get that, I want you guys to kind of fill in the code for this right here, okay? And remembering that we define this pos vector to be, exactly that. So remember, this pos vector contains the coordinates for all of the nodes in our mesh, okay? And so what I want you to do is I want you to use the pos vector, to fill in the coordinates for these nodes x1 and x2, okay? All right. And so the other thing that you're going to know is that remember the indices for each of the nodes, okay? And so if we're on the ith element right here, then to access the coordinates for the left node, okay? So we would do pos vector, and we go right here, and we can see that the index for node 1 is just going to be I, okay? So in order to get the coordinate for the left node, then we can do pos vector at IE, okay? And I want you to fill in kind of the equivalent code for x2 right here. So x2 will be pos vector at IE plus 1, okay? Okay. So was everyone able to fill that in? So we're just basically evaluating kind of the coordinates for the 2 points, okay? Okay. All right, so here's where things start to get a little bit difficult, okay? And so now that we have x1 and x2, and now that we have the Gauss points, GP1, GP2, and so the Gauss points, you can think of them as, what we're gonna plug into these shape functions right here, okay? So you can see that these shape functions are n1 of xi, okay? And so we have 1/2, so n1 in this case can be 1/2 1 minus xi, and n2 is gonna be 1/2 1 plus xi, okay? Right? And so what we need to do is we need to evaluate these at the first Gauss point and the second Gauss point, right? And so that's what I have right here for you right here. So we can see that xGP1 is going to be this function evaluated at Gauss point 1. Okay, and so the function that you need to plug in is going to be x1 times n1 of GP1 plus x2 times n2 at GP1. Okay, and then x GP2, it's going to be x evaluated at the second Gauss point right here. So we have x at xi2 is equal to x1 times n1 at xi2 plus x2 times n2 at xi2. Okay, and so once you guys go ahead and fill in the code to evaluate these guys. So basically for x, so remember for x GP1 right there, I want you to evaluate basically this function right here. Okay, and then for x GP2, I want you to fill in this equation right here. Okay, keeping in mind the shape functions given by this and the fact that we have x1 and x2 in these lines of code up here. Okay, and then for xi right here, we're going to plug in our Gauss points. Okay, so why don't you guys go ahead and take a couple minutes to fill that code in. Okay. Actually, did we finish our lecture notes from last time on Gauss Quadrature? That's what I'm thinking right now. Let me check. Oh, we didn't. Oh, you guys are probably wondering what the hell is going on because we never finished that example on Gauss Quadrature. Okay, so let me go back and do that after after we kind of get through this loop. Let's kind of fill in the rest of this here because we technically just from the theory of what we covered we can fill this in. But I think it'll be nicer to go through the hand calculation example too. So sorry about that. I totally forgot that we kind of left off at a weird place last week. And so let me get my iPad out while you guys are kind of filling in this XGP1 and XGP2. Okay. Okay. Actually, before we do that, let's actually kind of finish up our lecture notes. Okay. So I'm going to stop sharing this just because I think this will make a lot more sense after we kind of finish up that example from last time. Okay. Okay. So let me go ahead and stop this. Let me go to Zoom. Yeah, so if you need to evacuate, definitely get out of here. So everyone try to stay safe. Okay. Okay. And so where we left off last time, I think, was right after we computed the Jacobian, right? And so remember the whole idea with Gauss Quadrature is that instead of performing an integral that looks like this, okay? Okay. What we want to do is we want to simply evaluate this by taking a sum. Okay. Okay. And so basically this is going to be W1 of x of f of xi1 plus W2 f of xi2. Okay. And so remember the whole idea with Gauss Quadrature is that we want to avoid doing any integration and we simply just want to add, right? And so kind of just like a Riemann sum. Okay. Okay. And so the way that we did that is first thing we had to do is we had to perform a change of coordinates, right? Okay. And remember the reason we had to do this is that Gauss Quadrature only works It only works when the integration bounds are -1 to 1. Okay. Okay. And so our first step is going to be this guy. Okay. So we have our generic integral from x1 to x2 of f of x dx. Okay. And then we want to convert this into an integral from -1 to 1 of f of x of xi, okay, times dx d xi dx. Okay. All right. Okay. And so we know already, just from the slides that we went over, that x of xi is going to be x1 n1 of xi plus x2 n2 of xi. Okay. Right. And we know that this guy right here, dx d xi, this is going to be our Jacobian, right? And for these cases, I think we just finished deriving that our Jacobian is going to be x2 minus x1, all divided by 2. Okay. Okay. And so let's go ahead and do an example just to kind of show how this works. Okay. 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 And so for this example, let's say that we want to evaluate this integral right here, 200 times integral from 0 to 5 of 1 plus x squared over 400 dx. Okay. And so we this is an integral that we actually did, as part of our finite element forms example last time, and we know that the solution for this can be 1020.83. Okay. And so let's see if we can get the same solution from Gauss quadrature. Okay. Okay, so the first thing we need to do is we need to evaluate x of xi. Okay. Okay. So remember, x of xi here is going to be x1 times n1 of xi plus x2 times n2 of xi. Okay. We know from this integral right here that x1 is our lower bound, which is going to be 0, and x2, which is our upper bound, is going to be 5. Okay. Right. And so we can go ahead and plug those into this formula here. So we have 0 times n1 of xi, right? And so n1 of xi we know is 1/2 1 minus xi. Okay. That's just our shape function evaluated at xi is equal to for the bounds that we have. Okay. And then x2 is going to be 5, and then times n2 of xi, which is 1/2 1 plus xi. Okay. And so obviously, with the 0, this cancels out. So this is equal to 5 over 2 times 1 plus xi. Okay. Okay. And so now what we need to do is we need to compute the Jacobian. Okay. And so the Jacobian is dx d xi, which in this case is going to be x2 minus x1, all divided by 2. Okay. Which, if we plug in the numbers here, is going to be 5 minus 0 divided by 2 is equal to 5 over 2. Okay. Okay. And so what we can do now is we can plug these back in up here in order to evaluate this integral with Gauss quadrature. Okay. All right. Any questions on this so far? Okay. Okay. And so now that we have x of xi, and now that we have the Jacobian, we can go ahead and transform this integral. Okay. And so remember, our integral was 0 to 200, or 200 times integral from 0 to 5 of 1 plus x squared over 400 okay, dx, right? And so we want to transform this integral. And so when we perform a change of coordinates, our constant out in front will stay the same, okay? Okay. And so instead of integrating from 0 to 5, we're going to integrate from -1 to 1, okay? And so we're going to replace x with our expression for x of xi, okay? Because remember, after we perform our change of variables, we're going to integrate in xi instead of x, okay? And so instead of x squared over 400, we're going to have x of xi right here. And so our x of xi was 5 over 2, 1 plus xi, okay? Quantity squared over 400, okay? And then to this, we're going to multiply by our Jacobian, okay? So our Jacobian was 5 over 2, okay? Okay. And then we're going to be integrating in d xi, okay? All right. And so I think in the previous page, I might have said, this is dx right here, so this should be d xi. Sorry about that. Okay. So the whole point of the change of variables is so that we can integrate over a different variable, okay? Okay. And so now that we have the integral in this form, instead of actually performing the integral, we can actually just sum this guy up, okay? And so I'm going to simplify this. So I'm going to bring this Jacobian out in front. And so I'm going to have 200 times 5 over 2, okay? And then what I'm going to do is I'm going to evaluate this integrand right here, okay? So this is our integrand. And I'm going to evaluate it at xi is equal to minus 1 over root 3. And then xi is equal to 1 over root 3, okay? Okay, so let's do the first Gauss point first. Okay, so we're going to have, let me change the color. 1 plus 5 over 2 times 1 plus our first Gauss point. Our first Gauss point is minus 1 over root 3. Okay. Right. And it's going to be quantity squared all over 400. Okay. And so this right here is our integrand evaluated at our first Gauss point. Okay. Okay. And then to that, we're going to add our same integrand, but evaluate it at our second Gauss point, okay? And so we're going to add 1 plus quantity 5 over 2 times 1 plus 1 over root 3. Because remember, our second Gauss point is positive 1 over root 3 times 400, okay? And so this is integrand evaluated at second Gauss point. Okay. And all this is in square brackets. Okay. Right. And so from this, you know, if we actually evaluate the math from this, then what we get is 1020.83. Okay. And so you can see here, you know, with this Gauss quadrature integration, we get the same value as our exact integration. For this, it seems like we went through a lot more effort than simply integrating. But remember, Gauss quadrature is going to be something more for kind of multi-D, 2D and 3D integrals. So it's going to make things simpler for that. So I know for 1D problems, it just ends up being more work and kind of a hassle. But, you know, this is when you need to kind of practice it. Because remember, you know, when you're learning a new technique, it helps to practice on something that you know you're going to get the answer for versus, you know, just trying something completely in the dark. Okay. Okay. And so, you know, now that we've kind of finished this example, we can kind of go back and finish the code for this. So before I kind of switch back to the code, are there any questions on this? Okay. All right, so now we're back here. Okay. Okay, and so I think we left off right here. So you know, I want you guys to fill in the code to write xgp1, xgp2, and so that's kind of just like what we did when we you know, evaluated that before. So this is, you know, gonna be x1 times n1 of xi plus x2 n2 of xi. Okay. And so you do that for the first Gauss point and the second one. Right? And then from here, you can compute the Jacobian as well. Okay. And so our Jacobian is simply just going to be, you know, x2 minus x1 divided by 2. So go ahead and fill in the code for that. Okay. Right. And so now that you have xgp1 and xgp2, you can go ahead and fill in the code to compute this integral. Okay. And so remember, our integrand in this case, we're going to have two of them. And so our first integrand is going to be x squared times x2 minus x cubed. And then our second integrand is going to be x cubed minus x1 over x squared. Okay. And so now that you have xgp1, now that you have xgp2, and you have these integrands right here, go ahead and fill in the code to compute these integrands. Okay. And so remember, you want to evaluate these integrands twice. So you're going to evaluate them once at xgp1 and then another time at xgp2. Okay. And so overall, you know, because each integrand here has two terms, you should have 4 terms overall for each of these guys. Okay. Right. And remember that x2 and x1 here, you're not going to plug in. These are actually just the physical coordinates of here. So x1 and x2, you're just going to simply plug in this x1 and x2 right here. And it's only for the x that's by itself that you're going to plug in the GP expression for that. Okay. Right, so this part's probably the toughest part of this code right here. So definitely, you know, take your time, and if you have questions about it, you know, definitely, you know, ask in the chat or ask with your microphone.
The Jacobians using those same x1, x2?
Exactly, yeah. Jacobians using x1, x2. Mm-hmm. Okay. Right. And so I'll give you a little bit of a hint on how to start with this first one, okay? And so this first one, remember, we want to evaluate this first integrand here first at xgp1, okay? Because xgp1, that's going to be our x of xi function evaluated at our first Gauss point, okay? And so this thing starts with x squared. And so for x squared, we're going to plug in our x at gp1. Okay, so we have x underscore gp1, okay? And we're going to square that. And then to this, we're going to multiply our x2, which is simply just going to be our physical coordinate. Okay. And then from this, we're going to subtract xgp1 cubed, which is the second part of this one. Okay. And so that's kind of the first part of this integrand. So this is not the whole, you know, expression here, because remember, we have to evaluate this at xgp2 as well. Okay. And then you're going to do the same thing for the second half of this guy down here. Okay, which is going to be x cubed minus x1, x squared. Right?
Professor?
Yep. Mm-hmm.
Can you go over the Jacobian one more time?
Sure. So the Jacobian, the way that it's computed, actually I don't have it much here in the notes. The way that it's computed is simply just the derivative of x of xi, okay? And so we have this function right here, x of xi is equal to x1 plus n1 xi plus x2 times n2 of xi, right? And so the Jacobian is simply just the derivative of this with respect to xi. Okay, so we have dx d xi basically. And so, you know, x1, x2 in these cases, these are just going to be constants because these are just the coordinates of the nodes, right? And so those come out of the integral. And so the only functions of xi here are going to be n1 and n2, right? And so when we take the derivatives of this guy, we see that n1 here is 1/2 times 1 minus xi, and then n2 is 1/2 1 plus xi. And so if we take the derivative of this with respect to xi, we just get minus 1/2. And then for this guy, we just get positive 1/2, right? And so when we plug those in, as we said, we have basically dx d xi is equal to x1 times minus 1/2 plus x2 positive times positive 1/2. That's how we get x2 minus x1 divided by 2. Yeah.
Got it. Thank you.
Yeah. Right. So the question in the chat is treat the integral expressions like rows. That's correct. Yeah. So each of the different integrands here are different rows of this f element, right? So f element of 1, comma 1 i.e. is going to be you know, this top integral right here, and then f(lm) at 2 i.e. is going to be the second one right here. So x cubed minus x1 x squared. Yeah. Okay. All right. So everyone's able to get that. Okay. Oh, I actually have it right here. This might have been helpful to have. Yeah, so these are the expressions that I want you to plug in. So each of this x at xi1, this is going to be x at gp1, and this x at xi2 is going to be x at gp2. Okay, and so you can see the code that I've written here. You know, we have you know, this x gp1 squared right here times x2, and then from that we're going to subtract x gp1 cubed. Okay, and so you can see there's some additional stuff that I forgot here. So there's a 1 over LE out in front, and then a dx d xi as well. Okay, so make sure you remember those guys as well. Remember, this 1 over LE comes from our original shape functions, and then we also have this Jacobian guy. Okay, so don't forget those guys. Okay, and so that's going to be our heat generation integral, right? And so the next thing that we need to evaluate is the Neumann boundary conditions. Okay, and so our Neumann boundary conditions given by this guy. So we have n1 of x, n2 times a of x, q out, right? And this is evaluated only at the Neumann boundary. Right? And so if you remember, you know, the way that we did this for our hand calculations, finite elements, was that we only evaluated this at the element that bordered the Neumann boundary. Okay, so the majority of the elements are not going to have this expression right here. It's only going to take place on in this case, the rightmost element, because the rightmost element is the one that that borders the Neumann boundary. Okay, and so in this particular case, since our Neumann boundary is at x equal to L, this is only going to take place for the rightmost one. Okay, and so when we're forming our element forcing vector here, you know, we're only going to have contributions if our element is at the end. Okay, and so to kind of account for that, I've created this if statement right here. Okay, and so what I'm saying is if IE, so IE right here, that's going to be our element counter, right? And so if this is equal to something, you know, then we can apply our Neumann boundary conditions, okay? And so what I want you to do is I want you to fill in the code for this, okay? And I want you guys to keep it kind of general, okay? So what I saw a lot of in the last activity was kind of people were kind of hard coding in numbers here. And so if you guys knew, for instance, that, you know, we're using 10 elements, then we know that the last element was 10. Right? So you just put 10 right there. But I want you guys to write this code to be general, okay? And so, you know, make sure to put a variable here instead of just a hard number, right? So I'll go ahead and turn this back to do. All right. Okay. And so now that we've you've done that part, and so the next thing is to just simply add the Neumann boundary condition. Okay. And so if you remember, you know, the Neumann boundary condition is only on the rightmost node. And so when we evaluate these shape function terms right here at the rightmost node, and so in that case, n1, if we evaluate n1 at x2, which is the rightmost node, this is just going to be simply 0. And then if we evaluate n2 at x2, this is going to be 1, okay? And so that's how I got this vector right here, 0, 0, and 1, okay? And then to that, we're going to multiply A times Q out, okay? Right, and so the fact that, we're only going to have an entry for the second one means that we're only going to modify just one entry of the element forcing vector, okay? And so you can see from up here, when we did our heat generation term, we had contributions to both entries, right? So that both the top entry and the bottom entry. But for the Neumann boundary condition, because it only touches the rightmost node, we're only going to have contributions to the rightmost, to the bottom entry, okay? And so what I want you guys to do is to fill in the code for this in order to evaluate that. And taking note here that I'm using this form right here. So I'm using f of this is equal to f this plus an extra thing, okay? And remember what this does. So this is the notation that we use for assembly, right? And actually you can kind of see it down here too. And what this does is that it says to MATLAB that I don't want to simply replace what's in these entries right here, but I do want to add to it, okay? And so what this is saying is that f at this location is equal to whatever was in there before. So this is f element at that location before, plus the extra stuff, okay? And so this extra stuff in here is simply just going to be the contribution to the Neumann boundary condition. So this is going to be A times Q out. And then from there, I want you guys to kind of fill in what entry do you put into here, okay? And so it's either going to be 1 or 2 because, our element forcing vector is just a 2x1 vector, okay? And so I want you guys to decide, which one is good to there, and also to fill in, the extra contribution in that, okay? Okay. All right, so is everyone able to fill in the Neumann boundary condition? Okay. Okay, and so the next part after that, so once we've gone through this loop, our element stiffness matrix and our element forcing vectors are all set. And so at this point, we can follow the same process that we did before, okay? And so the next step is assembly. And so what we need to do is we need to add all these contributions to the global element stiffness matrix. And so I've written you most of the skeleton here. And so you can see that, I have this K global at, its certain entries is equal to K global at those entries plus KLM at the certain entries, okay? And so we've done assembly, many times before, and you've kind of already practiced this a couple times. And so why don't you guys go ahead and fill in the code right here, keeping in mind that, remember, our element stiffness matrix is only 2 by 2. And so that's why you only have 4 entries right here instead of 36 or 16, okay? And so why don't you guys go ahead and fill in the proper expressions, and noting that, for the global stiffness matrix, we need to put these into the proper rows, right? And so before, the way we did this was we used our connectivity matrix, but in this particular case, since our connectivity is so simple, you can just go ahead and fill in the proper, node locations here, okay? And so to get the row for node 1 of this element, you're just going to do I, which in this case would be IE, and then to get the second node, you're going to do IE plus 1, okay? Okay. All right, so was everyone able to fill in all the code for the assembly? And so you want to do both the element stiffness matrix and the forcing vector as well, okay? And so the forcing vector, you're going to use the same convention for the i's and IE's, and then you want to put the proper coordinates here too. Remember, the element forcing vector is just going to be 1 by 2, okay, or 2 by 1. So there's only 2 entries to it. Okay. So that's assembly. You know, assembly is the same as before, except in this case, it's a lot shorter because, you know, we have a lot less entries to worry about. Okay. All right. So after assembly is going to be our Dirichlet boundary condition. And so in this case, we just have one, you know, because we have a 1D problem. And in this particular case, our Dirichlet boundary condition is going to be on node 1. So that's on the very first row of the matrix. Okay. And so in here, I basically just have, you know, 3 lines. To basically satisfy this. So in this first line right here, you can see that this is going to set the first row equal to 0. This next row right here is going to set 1 on the diagonal of first row. Okay. And then this F global right here, so this is going to be new. So, you know, before, you know, for our structural problems, we always had the entry in F global to just be 0 for a Dirichlet boundary condition. But in this particular case, you know, we actually have a non-zero temperature here. And so here we're going to set our Dirichlet temperature. Okay. So you guys go ahead and fill that in while I answer this question in the chat. Okay. Okay, so the question in the chat is, what does this term represent right here? So this KLM to do IE. And so this is the entry in the element stiffness matrix that you want to add to the global stiffness matrix. Okay. And so remember, our element stiffness matrix is 2 by 2, right? And so we have a top left, a top right, a bottom left, and a bottom right. And so this KLM to do basically, you know, we want to add these entries 1 by 1. So let's say that we want to add the top left entry, right? And so this, in that case, we would do 1, 1 here, okay? And then you would add that to the appropriate place in K global, right? Oh, the third term. So the third term in this represents that particular element, right? And so what we did in this group right here is we solved for the element stiffness matrix for each of the different elements. And the way that we numbered them was we saved them to this entry right here, to this IE. And so the IE means that for the ith element, basically. Yeah. So it's the same syntax that we use for the frame element. It's just a way to kind of keep track of each of the different element stiffness matrices. Yeah. All right. So does that make sense of what the IE represents? Great. Okay. So hopefully the Dirichlet boundary conditions, you know, you can follow this, you know, you can follow very similar syntax to what we did before. Okay. And so for this one, remember we used a zeros command, and for this one we just had 1. And then for the F global, remember to set this equal to our temperature. Remember we have a variable for that. So our temperature variable is this T naught, which we haven't used up to this point. So make sure you use that down here. Okay. Okay. And so once we do that, we can solve. So I wrote this code for you just because it's the same as always. So we just invert F global, K global, and F global, right? And so if you've been following along and you filled in all the to-dos, you can go ahead and run the code, okay? And hopefully what you should get is something that looks like this, okay? And so I've already gone ahead and I've plotted the exact solution for you. So the exact solution here will be given in red, and then in blue is going to be the finite element solution that you just implemented with your code, okay? And so ideally, especially if you have enough elements here, so if you have something at least 5, then the 2 graphs should be basically right on top of each other, and you shouldn't see any difference. But if there's some errors, you'll see kind of a blue graph going one way and a red graph going the other way. Okay. And so you can basically use this to basically check your solution. So until your blue graphs and red graphs are lined up, you know, I would go back and check your code to make sure, you know, things are implemented correctly. Okay. So was anyone able to kind of fill in the code as we were doing it today and get the 2 graphs to kind of line up on top of each other? Right? So hopefully, hopefully you guys can get those guys to line up. Okay. And so this result that I'm showing you right here, this is particularly for 5 elements. So for 5 elements, that's kind of the lowest bar. You can see that we have a good lineup kind of on the left-hand side down here. And then once we get over to the right-hand side, it starts to deviate a little bit. So you see a little bit of blue kind of peeking out right there, okay? And so, you can definitely use this to check your work. So, if you're not getting these 2 graphs to line up, then there's going to be some issue in your code, okay? Okay. And so that's kind of this basic code. So that's kind of the walkthrough for this implementation, right? And so once you guys get that to work, then what I want you to do, so this won't be due, with this particular homework assignment. It's not going to be due with homework 3, which is the one that's due soon. But this will be for a future one. Is that I want you to kind of use this as a framework to implement, almost the same problem. But I'm going to change it so that you have an area function here that's going to be 0.1 plus x squared over 50, and then your your s of x, your heat generation, is instead of just being x squared, is going to be x squared sine of pi x. Okay, and so since you have these functions here, you're going to have to use Gauss Quadrature in order to evaluate these integrals. Okay. And so, if you get this first code working, then getting these ones to work, is kind of a step up. And so the biggest difference for this is that, for our element stiffness matrix, we didn't have to actually do any integration because our K and A were constant in this case. But for this homework assignment, your area is going to be a function of X. And so what I want you to do is, there's going to be a lot of changes in this loop right here that I want you to do to basically apply Gauss Quadrature to evaluate the integral for this A of X. Okay. Okay. So those are going to be your 2 things for this code. So the first thing is just to kind of fill out this code and to make it work with this exact problem. And then once you get that to work, then implement another code with these solutions, with these parameters right here. Okay. And then once you're implementing kind of the second code, you can delete all this stuff with this T exact. Because obviously, if the problem's going to change, then the exact solution is going to change as well. So you can delete that code there for your second one, but use this code to check your first code. Okay. Okay. Are there any questions on this code before we end the lecture today? Okay. So if there's no questions, then that's all I got for you guys. So we ended a couple minutes early. So thanks everyone for tuning in. Definitely, give this code a good look over, because, even though this is for a 1D case, this is going to form the basis for our 2D code, which is what you're going to be working on for your project. Okay. And so thank you guys for tuning in. I'll see you guys on Wednesday, and have a good evening, and stay safe out there. Thanks, Sarah. I got your email, so I'm going to modify your grade for that after this. Okay. Oh, I guess.
Professor.
Hi. How's it going? Oh, let me stop this. Hang on.